Hi, and welcome back to a last section of this unit on exponential and log functions, which is looking at differentiation and limits in these functions, mostly looking at differentiation. So 8.1 is differentiation of exponential functions, and 8.2 is differentiation of logarithmic functions. And so we're going to go through the derivatives of them and some practice with them, and you should be able to do some application problems like finding curve sketching, extrema finding, stuff like that. With the textbook on this, in 8.1 and 8.2, they go back and forth between differentiation and integration, and we're just doing differentiation again. Just remember that. So in the textbook, you'll have a little bit more things in there about integration. You don't need to know those things. So let's start off looking at exponential functions. So we'll use the limit definition to differentiate the function e to the x. So I want you to try doing this on your own. Use the limit definition. It's given over here. So remember that one. Try to go through the limit process on it and try to differentiate this function. Here's a hint for you that e is defined as the limit h approaches 0 of 1 plus h to the 1 over h. You'll need to use that somewhere in your proof. So pause this video, take some time for yourself to try doing this on your own, and then come back to the video and I'll show you how to do it. Okay, so hopefully you've taken a stab at this. Even if you didn't finish it, maybe you've made some inroads with it, right? And so now let me show you how I would do this. So I take f prime of x equals limit h approaches 0 of f of x plus h minus f of x over h. In this case, it's limit h approaches 0 of e to the x plus h minus e to the x over h. And now I'm going to notice that I have x plus h. When I have exponentials with addition on the top, I can split that up into e to the x times e to the h minus e to the x. Right, that's the same thing. And now I have a common factor of e to the x. So I can factor that out. So here's where I'm going to do a little trick. I know that the limit only concerns itself with h, right? It's the limit as h approaches 0, which means any term that doesn't have an h in it doesn't have to be inside the limit. It can be outside the limit. So I'm going to move the e to the x term outside the limit. And then go limit h approaches 0 of e to the h minus 1 over h. Here's where I'm going to use this definition now, because I have limit h approaches 0, so I can use the substitution directly in for e to the h, because it's the same limit as well. So instead of e, I'm going to write it as 1 plus h to the 1 over h. And then that's raised to the h minus 1 over h. So I've just replaced e with this 1 plus h to the 1 over h bit. And now notice that I have 1 over h raised to the h, so those cancel out. And so I'm just left with 1 plus h minus 1 divided by h. Well, 1 minus 1 is 0, and h divided by h is 1. So it's the limit as h approaches 0 of 1. Approaches 0 of 1, which is just 1, so it just becomes e to the x. So that's pretty fascinating, actually, because when we look at derivatives, usually we get a different function as a derivative of something. But in the case of the exponential function e to the x, its derivative is itself. It's e to the x. The rate of change of e to the x is e to the x. It's changing exponentially as an exponential graph itself. And that's really what contributes to exponential growth being so drastic and so big, because of that extra exponential growth rate as well. So from that, we can write our derivative of this. The derivative of an exponential function, d dx of e to the x, is e to the x. And remember to chain rule this. If there's a function in the exponent, so you'd go e to the u times du dx. So for example, if we had f of x is e to the x squared, then I want to find its derivative. I do e to the x squared times 2x, right, times the derivative of that inside function for the chain rule. Okay. So you have some practice problems on here to take derivatives off. I'll do maybe 2 of them, and then I want you to do the other 2 on your own. So let's do this first one. So y is e to the negative 5x. We want to differentiate with respect to x. So I want to find dy dx. So to start off, the derivative of an e function, exponential, is just itself. And then I multiply the derivative of that function in the exponent, negative 5. And I can clean this up and write it like this. Let's do c, because b is similar to that. It's a power rule. C and d, that's where you're using some product rule and quotient rule again. So remember those rules that you learned back last semester and you did with trig earlier on the semester. All of those rules still exist for taking derivatives. So you should know your chain rule, power rule, product rule, quotient rule, and so on. So in this case, this is a product rule. So when I take its derivative, I take the derivative of the first function, which is the derivative of x, which is 1, times the second function, times e to the x, plus the first function just like itself, times the derivative of the second function, which is still e to the x. And so I get e to the x plus x e to the x. If you were solving this, right, if this was equal to 0, you were trying to find critical numbers, then you might want to factor this like that and set it equal to 0, because that will make it easier to solve. So that's something that you might do depending on the type of problem you have. Next, do b and d on your own. Next problem here is finding the equation of the tangent line. So tangent line is, you need to know the derivative because you need to find its slope there. So let's find the derivative of this function. So I have e to the negative 2x plus x squared, and I multiply the derivative of that inside function, which is negative 2 plus 2x. And I need to evaluate this at the point 2, 1 to get the slope of the tangent line. And so this would be e to the negative 2 times 2 plus 2 squared times negative 2 plus 2 times 2, which is e to the negative 4 plus 4 is e to the 0, times 2 times 2 is 4, minus 2 is 2, so the slope is just 2. And I go y minus y1 equals slope x minus x1. And I get the equation of the tangent line. Next problem is, again, reminding yourself about different types of derivative rules. We have implicit differentiation. So here we're differentiating this implicitly. We're not going to just make it y equals. It's difficult to make it y equals because you have a y up there. So we're just going to take the derivative of everything on both sides of this equation. So e to the xy, derivative of that is e to the xy, times, now the derivative of x times y, that's a product. So I'll have to product rule this. Times 1 times y, so derivative of x times y, plus x times the derivative of y. Then I go on to the derivative of x squared is 2x, and the derivative of y squared is 2y dy dx. The derivative of 10 is 0. Now I need to solve for dy dx. I'm going to try to isolate it. I'm going to expand this out. And then I can move all the non-dy dx terms to the other side and divide out the things that are multiplied to the dy dx's. And I get this expression as my derivative. So that should give you a sense of taking derivatives of exponential functions. So I'm going to pause this video here so you have smaller chunks to look at, and then I'll make the next video to go on to the log functions.